So as described, HMM can be mapped or represented in terms of three parameters, A, B, and pi, where A represents the state transition probability, B represents the bias probability or the emissions probability, and pi represents the initial probability. So in the case of, say, gesture recognition, the state will be represent, or a particular state will represent a pose. For example, here, this is a hand waving gesture as an example in terms of motion taking place. So with this particular pose or state, then let's say in terms of the distribution of the feature would be looking like this, where as obviously, as you can see, the direction of the fingers is represented by this. In other words, if you can kind of think of the direction being 0 versus, say, plus 90 versus the negative 90 degrees, this way. So this would be, say, 0, and this would be plus 90, and this would be the negative 90. So most of the direction of the fingers lie in the negative region toward the minus 90. And similarly, when this pose, which has most of the fingers going up, so it is situated, say, around 0, mostly distributed around 0. And this particular pose with all the fingers pointing toward this way, so most of the distribution of the fingers in terms of the direction lie in the 90, plus 90 region. So this means that you could have each of the pose as being state, say state 1, state 2, and state 3 has its transition probability because you're making a motion, say with this particular palm or hand with a motion waving, which makes the hand sort of like being rotated in the clockwise direction. And as a result, the way how the feature set, which is extracted by, once again, looking into the direction of the fingers and their distributions, can be extracted by, say, in terms of the distribution here. So you will have distribution for each of the state, which is represented by B, and together the entire say HMM representation by using A, B, and pi with, say, 3 state. Here obviously it's got the 3 state transitions or HMM model in the state diagram case. It could actually map a certain say word, like say the word the high, or you could also say a slightly different variation of this to mean that it's a goodbye. So you can map any of these hand waving, any of these words in terms of hand waving, where each of the hand waving can be represented by different HMM models, where HMM models, as I said, would be described, represented in terms of 3 parameters, A, B, and pi. Okay, so just to delve into HMM a little bit more detail, here's the way how Rabinor in 89 has described the HMM model. And he described this in terms of, once again, urns and the marbles. So here in the HMM has 3 states, meaning that it's got 3 urns. So state 1, state 2, and state 3. And then there's another set of, say, urns to represent the state transitions. Well, actually, these represents the state transitions, and this one represents the initial probability. So to make up for, once again, the entire HMM model, it's going to require A, the transition probability, B, the emission probability, and pi, which is the initial probability. So A is represented by these three urns, where each of the three urns contains say these urn numbers, so that it can describe the transition probability. For each of the state, it's got the emission probability or the bias probability, meaning that at each state there's an urn that contains the different colors of the marble. So you have a different colors of marble here for state 1, and another one for state 3, and a different set of the color of the marbled colors in, say, state 2. So these are, say, B here, and this represents A, and this represents the initial probability. So how this thing works is as follows. So you have this HMM model in the as you can see, in these connecting model representation, where on the right hand side you have these urns for state transition probability representation. In other words, each of the urn, for example, say state S1, has these number of other urn numbers, and these urn numbers represents essentially a transition probability. So for example, though, how this works is that with a pi, a person would draw say a number or card. Let's just say that these represents cards, C-A-R-D. So each of the number represents cards. So randomly, a person draws a card out of this urn, and then looks at the number, and that number, if it says say number 1, because obviously you have a lot more ones than compared to other ones. So he would look into this urn, and then also pick a card randomly out of this urn. So that number is going to actually, if it says 2, then he goes to say this urn, and subsequently he randomly picks another number, and then that number, let's say if he says 3, then it goes to number 3, and so forth. So this thing is repeated for many times, and essentially the way it is going to be done is that this person counts the number of occurrences of making these transitions. So that's where the A is going to be established, having say 3 urns with all these 3 different card numbers in there for each of the urns. And similarly, the pi can be described by, once again, having this urn with a set of these cards with a certain ratio being represented by the number of say urn 1, number 2, and 3 in terms of the card number. And B is reflected by these urns with having a specific number of marbles with different colors. So in this example, so 3 is the number of urns, and M would be the colored marbles. In other words, the observations of the observations would be these colored marbles, either white, black, light blue, or dark blue. So they represents the observation symbols. So M would be equal to 4. So in other words, you would have some sort of distribution having, let's say, this particular urn having, say, some sort of distribution looking like that, right? So this would be, say, white. This would be, say, black, light black, light blue, and dark blue. So some sort of distribution looking like that. And similarly, you would have a different distribution to represent, say, this particular urn, and so forth. And you would have another one like that, like this, to reflect the distribution of the marbles for each of the urn, where the urn represents these state. So Rabino described it in terms of taking an experiment, which is exactly what I just described. So, for example, you draw a card from the pi urn, the initial probability urn, and note the card number. So, if and that would be the state number. So, for example, urn number. So, if it says say number say 1, so that would be a state 1. So he draws a colored marble from the marble urn corresponding to the card number. So that means that if it says S1, state 1, he draws a colored marble out of this urn and record the color as observation 1 and put it back. And then draws a card from the card urn. So this is the card urn. And then note the card number. If it says, say, number 2, let's say if it says card number 2, then he goes into so, and then we note that card number, and that note card number would be say number 2 in this case, right? Because it's S2. So we repeat this process 2 and 3, and record all the observation sequences as well as the urn number sequence. Only thing is that we should note should be noted is that we can see what we can see would be the observation sequence, but not the urn sequence. So the question here is this: if the observation sequence happens to be this red, white, white, black, red, white, white, black in this sequential order, then two questions. Then what is the probability of this sequence? And then the second question is what would be the corresponding state sequence, number 2. So in other words, a specific observation has taken place in sequence. Then what is the probability of that sequence, number 1? And number 2 would be what is the corresponding state sequence. So essentially, this is what we are actually heading. So given a certain observation sequence, and we just saw with that hand waving motion, given, say, a specific order of these features from the hand waving in, let's say, a certain sequence of the observation, what will be the corresponding state sequence? That is, remember you saw the hand motion having certain direction of the fingers going to pointing to the left and pointing to the top, upward and pointing to the rightward and so forth. So this is what we need to extract as a process, as a problem of the HMM. Now, to describe that process a little bit more, let's use an example. Suppose you have a person, and we have the privilege of observing this person's life log under various weather conditions. So the life log would consist of this person's actions like walking, shopping, and cleaning. So 3 are the possible observations that you can do. And the state, the weather scenario would be either sunny or rainy. And then we have based on the information database on A, we can establish this HMM model. So in this Markov chain model, we have, for example, 2 states, rain and sunny, and it's got all the transition probabilities as well as the emission probabilities for each of the states. So in other words, In other words, as far as the state is concerned, state transition is concerned. So this would be, for example, today being rain when yesterday was rain. So the probability, the conditional probability of today being rain, conditioned on yesterday being rain, that's like 0.7. And similarly, you have given rain, the probability of today being sunny, that would be zero point 0.3 and so forth. So you have this zero point 0.3 and this being 0.4, and the self loop would be 0.7 here for rain, and the self loop for sunny would be 0.6. And once again, for each of the two states, we have the emission probabilities, meaning that the probability of having three of these or one of these three activities is shown here. For example, this person walking while raining would be, say, 0.1, and under the state of, say, rain, and the probability of shopping would be, say, 0.4, and this person under rain cleaning would be 0.5. And for sunny, under sunny, the same person, right, walking would be 0.6, and under sunny, shopping would be 0.3, and under sunny, the activity being clean would be 0.1. So now we have a complete HMM model. Well, I missed out the initial probability. So let's just say that in terms of the weather, the 60% of the weather happens to be rain, and 40% of the weather happens to be sunny. So these are the initial probabilities for the states. So now the HMM model has all the essential components, essential parameters: the transition probability A, the emission probability B, as well as the initial probability. So once again, given this model, can we answer the following questions? What is the probability that this person goes to shopping 7 days in a row? So observation happens to be shopping, 7 days in a row. Okay, and if, however, this person does observation walking, walk and clean in this sequence for 3 days, what were the weather for each of the day? So that weather, I'm going to be describing it as, say, Q1, Q2, and Q3. So this would be the weather sequence or state sequence. So two questions once again. What is the probability that I goes to shopping for 3 days or 7 days in a row? And given that this person, so this is one question. And the second question is, given the observation sequence being like this, what is the state sequence? Okay, so here we can obtain the probability of using a HMM model. So we have the entire HMM model once again. HMM model, say, theta, consists of A, B, and pi. So this is what we're going to do. We're going to actually perform an answer to these two questions. Number one, probability that A goes through shopping 7 days in a row, and number two, given the sequences observation for 3 days, what were the weather for each of the day? So we're given a task. We were asked for, what is the probability that this person goes to shopping for 7 days in a row and so forth. Now that particular problem, given a model of an HMM model of A, B, and pi, uh, observation sequence being like this, then computing this the probability of this observation sequence is called evaluation. So that's one of the three fundamental tasks that we need to do using HMM, or three basic problems for HMM. Another problem that we can solve is that given the observation sequence O and the model, given this and say particular observation sequence, we can then also calculate and obtain the corresponding state sequence, which is optimal in some meaningful sense. That's going to be called decoding process, or the task of obtaining optimal state sequence. And then the third problem for HMM is that we need to be able to actually build A, B, and pi. So this building process is called training. In other words, with having the data set, we can actually train and then establish these parameters. So they are the parameter estimation problem. So once again, we say that there are three basic problems for HMM. One is evaluation, that is given a certain observation sequence. We can then obtain the probability of that observation sequence given, once again, a specific HMM model. And second thing that we can do is that we can decode, meaning that given a certain observation sequence and the model, HMM model, we can then essentially obtain the corresponding state sequence. This is the decoding problem. So once again, given what this means, the decoding means is like speech recognition. So given, say, a sequence of some features that's taking place over time, then this decoding process will allow you to be able to obtain the sequence of the decoded state, where the decoded state in the case of speech recognition would be the decoded, let's say, phonemes. So, for example, the phoneme would have, its own state. So that would be the state sequences, or phoneme sequences, which would be, once again, essentially be the component of the automatic speech recognition. And then the third task or problem for HMM is, once again, how do we then obtain this HMM model? That is, we need to establish A, B, and pi. So therefore, we consider this as a training process whereby these parameters are estimated. Okay, so let's just say that, let's just delve into the three basic problems for HMM. In terms of the architecture, the HMM can be expressed in many different forms of a graphical model. The nodes here represents the states, and you can have either ergodic or left to right model, where the ergodic model, as you can see, has all the states connected to each other, including the self-looping, whereas for the left to right model, it goes to just one direction, left to the right. It doesn't, for example, like go back, like in the ergodic process. So you could have like this type or this type for the left to right model. Typically, it would be looking like this for speech recognition model representation. Okay, so to do the three basic problems, once again, let's just identify what they are in terms of the three parameters. So I said three parameters being essentially the transition matrix A for HMM. So this is HMM model theta, which is represented by A, B, and pi. So A would be the transition matrix, meaning that we said that it would be denoted by A sub ij, which means that it's the conditional probability of, say, at the state at t plus 1 being state s sub j, given that the previous time state being at s sub I. And the entire every say every um, every connecting transitions that leaves out of the state, the sum would be equal to 1. And the observation matrix would be, or actually observation vector in this case would be the vector for each of the state. So for example, b sub j of vk means that it would be the conditional probability conditioned on the specific, say, state. So at that state being at time t, being, say, jth state, given that state, it would be the probability of the observation at time t being symbol v sub k. So that would be represented by this b sub j of v sub k. And the sum of all these emission probability or observation probabilities would be equal to 1. And we also have the pi here, which is the initial probability vector. So this would be the initial probability or prior probability for each of the states. And of course, the sum should be equal to 1. So these are the three parameters representing an HMM model. So once again, we have just to remind ourselves that we have three basic problems for HMM. One is the evaluation, that is, given a observation sequence, what is the probability of that observation sequence? Decoding is that given the model and also given the observation sequence, what is the optimal state sequence? And third is the training. So given the training data, what is the HMM parameter models? What are the HMM parameters? So this will be the training process. So typically, when we do the evaluation and decoding, we use the dynamic programming because it's going to allow us to make it much more efficient, because it could be very, very tedious process. So for evaluation and decoding, we use the dynamic programming. For training, we do it using the EM algorithm, or expectation maximization algorithm. Okay, so let's move on to each of these elements. Number one, evaluation. So evaluation is the first of the three basic problems. So what is the evaluation problem? Given a model, HMM model theta, and if observation sequence O is known, what is that what is the probability of that observation sequence? For example, what is the probability that this person A continuously shopped for 7 consecutive days? So to solve the evaluation problem, once again, we are going to resort to dynamic programming, but just to be able to show a motivation for that, let's just go through how we could actually do the evaluation. In HMM, we don't know the state sequence. All we know is just the observation sequence. Uh, if we did know the state sequence at the same time that has produced the observation sequence, then the problem would be much easier. However, we don't have that information. But assuming that we do know that produced, say, observation sequence, then we can derive the following equation, right? So in other words, observation sequence, and then Q would be the corresponding state sequence. Then this would be the essentially the probability of the observation sequence, as well as at the same time simultaneously the state sequence. Being, for example, we start off with the initial state with that probability, and then that's going to be multiplied by the specific observation, at say state Q1, and then at that point there's a state transition from Q1 to Q2, and then we have this emission probability at that state Q2 with this specific observation, and so forth. So we have then up until say OT as the last observation being. So we can compute the evaluation. We can compute this probability if we have this information, this state sequence information as well. Then we can obtain the observation sequence, the probability of the observation sequence by summing all possible Q, right? All possible Q as follows. So this is actually, right here. So this is actually summing all possible Q is going to give you this marginal probability. With a joint probability given joint probability, if you sum all the Qs, then it's going to give you the marginal observation probability. Anyway, so returning to the life log problem, once again, what is the probability of A that he walks today and walks tomorrow and cleans the day after tomorrow and shops 7 days later? So this means that the observation is that today he walks, tomorrow he walks, and third day he cleans, and then say shops after that. So this would be the observation sequence. So given this observation sequence, what is this probability of that observation sequence? Once again, using the HMM model here. So this is the HMM model theta. And so the way we are going to do is that we are going to arrange for all possible sequences for, say, rain and sun. So for example, so this is the trellis diagram that actually reflects what could happen in terms of state as well as observation. So this person has obviously observation 1, observation 2, observation 3, and observation 4. The first observation that this person will do is walk, and second would be the walk, and third would be clean, and fourth would be shot. So this is the observation sequence. And then out of the observation sequence, possibly that this person could be either under rain as well, or this person could be under, say, sunny. So either rain or sunny. So all possible observations, observation sequence for the 4 days, it could be just, just rain, 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 rain. So rain, 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 or it could be rain, rain. So rain, 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 and then rain, and then sunny. And so many of these variations, right? Rain, rain, say sunny, and then rain. Um, so counting all these possible state sequences, there are, as you can see, 16 possible such state sequences that could produce these observations. First day being walk, the second being walk, third being clean, and the fourth being, say, the fourth being shopping. So this means that, let's just say for just using maybe four straight rainy days. Let's just obtain the state sequence being rain, 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 which would be the Q1 case. So with that, and then at the same time, observation sequence being this. Okay, so this is the computation of the joint probability of the observation sequence being this. At the same time, the state sequence being this. So with that, we can actually compute that process. So here, the first would be rainy. So we said that the initial probability of rainy day would be 60% or 0.6. And then under rainy, the probability of walk would be 0.1. And then rain to rain, the transition probability would be 0.7. And once again, the probability for walk, just like before, would be 0.1. And once again, the transition would be 0.7. And then the third day would be clean. So in that case, the probability of clean under rain would be 0.5. And then here we have, once again, it's a rain to rain. So transition is 0.7. And then it is multiplied by, say, shopping, which would be, say, 0.4 under, say, shop under, say, rain day. So if you multiply all these things, this is the value. So you could actually evaluate the probability. So this is that evaluation of the observation sequence. So you could do the same for all other cues. So there are 16 possible combinations of the rain and the sunny day. And if you sum for all possible state sequence, this is going to be the result. So this is represents the case for the rain, 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 rain. This represents for the case for rain, 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 and the sunny, and so forth. So, and then the last one here would be the sunny, 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 sunny. And if you add all these combinations, the result is going to be 0.0111. So this would the probability of the observation sequence being this. So this seems to be okay, but seems like it's a little bit tedious um, for, let's say, even having four with two state combinations with four, say, time point. That's going to give you about 16 different combinations of state. So this means that if the state number is n and the observation O sequence is capital T, then we are going to have a huge number of computations because there are, first of all, n to the t possible state sequences. So this state sequence, as we saw in the previous slide, is going to take actually t minus 1 multiplications. This means that the complexity is actually nt power times t. So this means that in terms of the number of multiplications, for n being 5 and t being 30, that is 5 different states with, say, amount of time being t being 30. So that would be 5 to the, let's say, 5 to the 30th power. And this is going to be, well, actually 30 minus 1. So this is going to be 5 to the 29th power. So this is going to be a huge number of multiplications. Just too many computations. So maybe there could be an easier way, a little bit more efficient approach that could exist. Here, the efficient algorithm, the basic idea is to get rid of the repetitions by using something called the dynamic programming. A case in point here is that, let's say, Q1 versus Q2, we are seeing 3 R's being repeated for both Q1 and Q2. So you have 3 R's being here, another 3 R's being here as well. So this means that you actually have a repetition for being this much, being exactly the same for, say, Q1 and Q2. So maybe we can alleviate that. Maybe we can alleviate that and just maybe exploit this repetition. And how we could do that is by using, once again, a dynamic programming. So what's a dynamic programming? Let's make an observation here. So this is the trellis diagram of the process that we just described, that is having, say, 4 state sequences or 4 observation sequences of the 2 states. So being, let's say, the rain versus that of the sunny. And so this trellis diagram sort of expresses the all possible 16 possible state sequences. Once again, we could have, say, rain, 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 and rain. So this will, if you go through this path, this means that you have rain, rain, and rain. You can also have, let's say, Q7 going, say, rain, sunny, sunny, and rain. So this would be, this particular path here would reflect that of Q7. Now, what we want to do is to represent the dynamic program's alpha representation, where alpha sub t of j, which is this, represents the probability of observation sequence from O1 to OT at time t under state, say, S of j. Once again, this alpha sub t of j represents the probability of the state of the observation sequence from 1 to t at time t under state S of j. This means that the observation sequence and the state needs to be jointly stated or jointly reflected in this probability. Now, this is going to be actually equal to, as you can see, a iterative process, where that iteration is going to be represented by this, meaning that, as you can see, that the observation sequence, the probability of the observation sequence from 1 to t here is going to be equal to the sum of the sum of the same alpha of the previous time times the state transition probability of I to j multiplied by the observation probability at the time t, where this j is that of say state j. Okay, so that's sort of like the mathematics. And just to describe this in a diagram, let's just say that you are at t here, time t, and this is t minus 1. And at time t, this is the state, where this node, as you can see, is represented by a sub t of j, meaning that you are at the node at state, say, j. So this is actually state j here, where, once again, this subscript t represents the time point, and this alpha here is alpha sub t of j, is the sum of all the previous alphas multiplied by the transition probabilities between this node and the previous nodes. So each of the node at the previous time, t minus 1, is multiplied by the transition probabilities. And at the same time, the last thing is that we need to multiply this node representation by the probability of the observation of t at, say, state j. So that's what this is. Meaning that, once again, all the information that was taken at the previous time, t minus 1, can be then accumulated into forming the information at the node of j at time t.